All right, so this is the Unit 1 study guide, and we're going to go through the different objectives. I tried to highlight these on your midterm exam, so I hope you find this is helpful. The first thing was to define mass. I'm going to pause the video so you have a chance to go ahead and write down your definition of mass. All right, you should have said mass was the amount of stuff in a sample or something close to that. The next thing is, what are the units of mass? Whenever we're talking about the mass, we're always measuring the weight of something, and we measure it in grams. We could measure it in pounds or kilograms or other units. The base unit that we use in science is grams. The next one is volume. Go ahead and see if you can come up with a good definition for volume. Also, name the units for volumes, and we use 2 of those. Okay, you should have said something about the volume being the amount of space taken up by a sample. And then we use 2 different units, milliliters or centimeters cubed. Remember, 1 milliliter is equal to 1 centimeter cubed. On your midterm exam, you're not going to have to demonstrate that you can use a multiple beam balance to determine the mass of various objects, but you will need to be able to understand and express your understanding of why significant figures are important. So take a second now, and how would you express why significant figures are important? Because we do seem to use them an awful lot. Significant figures are important because they represent the accuracy of the measuring instrument you're using. Let's say that you're taking the temperature of something and you've got one thermometer that only measures things in units of 100 degrees Celsius. So your thermometer starts at 0, and then it goes up to 100, then 200. So the marks on the thermometer are 100 degrees apart. You'll see this on sometimes some cooking thermometers and candy thermometers. They have very large separations between them. Well, if you're using a thermometer that only has markings that are 100 degrees Celsius apart, that's not very accurate. If you're using a thermometer that has markings that are 0.0, that's more accurate. And of course, if you have another thermometer that measures to the hundredths place, these are all in degrees Celsius, this would by far be the more accurate thermometer. When you're counting your significant figures in this one, you would start, there's no decimal point, so we would start from this direction. We'd go and we would have 1 significant figure. For this thermometer over here that's in the middle, again, decimal is present, so we're going to start from this side. We start with that first 0 and we count till we run out. So 1, 2, 3, 4. This one has 4 significant figures. It's a lot more accurate than that thermometer that has only 1 significant figure. And our last one, the decimal's present, so I'm going to start from this side. My first number is a 1, and I just count until I run out. So 1, 2, 3, 4, 5. This has 5 significant figures. So when I'm doing all my calculations, and I'm using this thermometer that has 5 significant figures, I know I can count on my results to be far more accurate. Now, remember, a histogram is where we're counting the number of samples. So here's the number of our samples, and here's usually we started at 0, and we would have +1, +2. We did the sugar experiment with, how much mass did you lose? Remember, when we're doing a histogram, we're counting the number of times you get a result. We used also the example of grades. But if I have number of measurements, if I had 5 measurements, I'd have 5 different groups that do an experiment. If all 5 of them get a difference in their measurements of 0, I would go ahead and graph that with a bar of 5. Let's say that I had 3 groups that got a +1. There we go. Let's say that I had 3 groups that got -1. And I had 1 group over here that got +2. That would be an example of a histogram. Ooh. Not on test. Now, every single one of those experiments we did, we always were looking actually at the law of conservation of mass. Go ahead and take a second and write down, what is the law of conservation of mass? So mass is a measurement of matter, and we know that matter is not created or destroyed. When you're doing an experiment, the weight will not change when you're comparing the initial and the final. When you're looking at mass, you'll always have the same amount or the same weight of the reactants as you will the products, and we'll see that more clearly as we move through some chapters in the future. This is a really short one because I just kind of answered this one earlier. Relate the volume of a container in centimeters cubed to the volume of liquid it contains in milliliters. We did that experiment where we measured containers and calculated the volume in centimeters cubed, and then we measured the amount of liquid using milliliters. And we knew our calculations were right on if our calculated value matched the milliliters that we read in the graduated cylinders. 1 milliliter equals 1 centimeter cubed. This next one goes back to what I described about significant figures. All instruments have limits to their precision. So that's why we need to keep track of the significant figures. There are, with very few exceptions, there are very few numbers that we consider to have an unlimited significant figures. So because all measuring instruments have their limitations, we have to consider the significant figures when we're doing our calculations in chemistry problems. It's different than math situation in math where you're not concerned with what measuring devices were used. Whenever you're doing science, we want to reflect, hey, what kind of device was used to measure this experiment and how accurate can we be in our reporting our results. The question itself kind of answers what's a question that's probably going to be on the test, and that is, what mathematical operation do you use when you're trying to determine the appropriate number of significant figures? All right, so the operation you need, it says right there, you have to round your calculated answer to the correct number of significant figures. Let's say you've got this number I've written here, 13469.72, and you need to have 3 sig figs. So decimal is present, so I'm going to start on this side. So here's my first significant figure. Here's my second one. Here's my third one. I need 3 significant figures, so I have to look to see what is the next number that's behind that. The 4 is followed by a 6. So we use regular rounding rules. If it's 5 or more, it's going to cause that 4 to become a 5. So the new number will be 1, 3, 5, 0, 0. That will have 3 significant figures. The 6 becomes a 0, the 9 becomes a 0. These go away because I only need 3 significant figures, and this 4 becomes a 5. You're just rounding and then keeping the number. Do not amputate your number. Never just chop it off so you have the number of significant figures. We want to round your answer. This answer here is reasonably close to our original number. If I chop that off and just call it 135, that's extremely different than my original number. 135 is very different than 13,500. All right, the next question says, given a graph of mass versus volume of a substance, write the equation of the line and state the meaning of the slope. Go ahead and draw a little line graph with the mass versus volume of the substance. And let's see what we can do. We'll just do the equation for the line, and we'll talk about which value is the slope. All right, so here's an example of a mass versus volume graph. As mass increases, the volume will increase also, because I have more space that's taken up by the stuff, which is measured in grams. The formula for the slope of the line is y equals mx plus b. So I can substitute these numbers in anywhere along this line and find the equation for the line. Your slope will be b. B will be measured, the unit for B will be in grams per milliliter, or our other unit for volume, centimeters cubed. So anywhere along this line, I can read the number of grams per milliliter cubed. This value here is very important because for this substance, what I'm really looking at here is the density. So the slope will equal the density. And it's actually kind of nice because when you're looking at one of these graphs and you're given all these numbers, you'll actually see the unit of grams per milliliter or grams per centimeter cubed, and that's the kind of units you're going to have for density. So density is a characteristic property of matter. Different substances will have different densities, and they're very specific to that substance. Water has a specific density. Iron has a specific density. Any of the elements on the periodic table are going to have their own densities. How much space will be taken up by a gram sample of the substance? Now, right now, take a break here for a second and write down what is the formula for density. All right, so here's a density question for you to try to solve. If you have 10.0 grams of a substance whose density is 3.15 grams per centimeter cubed, what will be the volume of the sample? Go ahead and stop the video and give it a try, and I'll show you the answer. All right, so what you should have gotten was 3.17 centimeters cubed. Basically, we're just solving for our unknown. Now, you can also use density as a conversion factor between mass and volume. Let's do the same problem as using it as a factor label problem. So to do this, I'm going to start with my known, 10.0 grams. Now I can look at my density as a conversion factor in the same way that I'd convert grams to kiloliters, or kilograms to grams. So if I have gram on the top, I need gram on the bottom. There are 3.15 grams per 1 centimeter cubed. My units are going to cancel out. And I'm going to come up with my same answer, which is 10 divided by 3.15, which would be 3.17 centimeters cubed. So you can do it either way. You can either use the density, set it up as a where you're converting for an unknown, looking at the proportion, or you can set it up as a factor label problem, whichever one. Both will work out with the right answer. So the last one leads us right into Chapter 2, where we were doing a lot of particle diagrams. So right now what I'd like you to do is to draw 3 boxes. And you're going to draw particle diagrams, which we've been doing all along. Those are some terrible boxes. Let's draw some better boxes here. It's a little better. Still not great. There. That's better. This one I want you to draw a solid. This one I want you to draw a liquid. And this one I want you to draw a gas. Now, the thing we want to do here is we want to draw our pictures so they're consistent with the densities, which is going to be the most dense, the middle density, and the least dense. And again, we're not going to think about water, because remember, water is the tricky one, where the liquid form is actually more dense than the solid. All right, this is what it should look like. We've got very organized pattern in our solid, less organized in the liquid, and much less organized in the gas. We've got particles packed closely together in the solid, less tightly packed in the liquid, and very little degree of packedness for our gas. Well, that's the end of this video. Didn't take us that wasn't too bad. Hopefully you found it helpful, and this is summarizing all the things we did in Unit 1. This should follow very closely with what's on the midterm.